Hello, hello, hello. What's up? What's up? What's up? We're back with a new video. This is the end of our stream. This is the end of our experiments. This is the 12th experiments we are going into. Okay, we have done with 11 experiments before. Some of MATLAB, some of LabVIEW, two of virtual labs. We are going into the third experiment. We will be starting now, which is the analyze the transfer function and portfolio plot of a control. This is in virtual labs. Okay, so I will give you the aim, the software and theory, and then we'll go move toward the software part. I will teach you on the screen itself. So aim to obtain the pole zero plot from a given transfer function and also to find the transfer function from given pole zeros and gains. I will explain you everything into this. And then there is software, that is virtual labs, and the core concept. This experiment teaches the relationship between a system's transfer function and its portion is zero. So transfer function is a mathematical representation of a system's input-output relationship, specifically ratio of the output Laplace transform to its input Laplace transform. Zeros and complex frequencies, values of S that makes the numerator in the transfer function equal to 0. Poles are the complex frequencies values of S that makes the denominator of the transfer function equal to 0. This is the theory part. If anyone needs need these in the exams, they can use it. Okay, so then we come to this part. So see, there will be the user inputs and there are coefficients of denominator polynomials. First, we will give some input, some kind of inputs. If you want to give like this, you can go into minus, you can go into positive, you can go into again negative, then again positive. So here we do submit. Submit after then we get the number of zeros, that is 2. We get the number of poles, that is 2. We generate the transfer function, that is 4s squared plus 2s minus 3 by 4s squared minus 2s plus 6. Then the uptrend the poles, zeros, and the gain values, that is minus 1.15, 0.65, poles is 0.25 plus 1.2. I is the imaginary number, and then 0.25 minus 1.2 I, that is the imaginary number, because we always know that imaginary comes under a root, that is plus minus b. If you remember the formula, uh, b plus minus root of b square minus 4ac by 2a, this is the formula we use it. And then there is our k, that is our gain, that is 1, and plot values on the graph. This is the values plotted on the graph. Our x are the poles, our green color zeros are the poles or the zeros. Okay. So the conclusion, as two poles of the system lies on the right half of the S-plane, therefore the system is unstable. So anyhow, if the two poles are on the right side of the S-plane, then therefore the system is unstable. If they were on the left half of the S-plane, then the system was stable. We can try to bring this on the left half. Let me try. So we run it. It's again on the right half. So somehow we figure, I think so we need to make it up to bring it on the left half of the system. Something like that is there. I'm not sure. Yeah. So to bring it on the, we need a proper values to bring it on the left side of the system. But yeah, the zeros are moving. We can see this. We can see the values of the zeros. And for the poles, they are mostly at that same point only. We need to change. We need a perfect value to bring it on the left side of the system. I think so. This is what it was for this experiment. Experiment number 12. We are finishing this series. Have a good night. Goodbye. It was good working with you guys. It was good learning with you guys. We will try to continue this channel much more. And yeah, thank you. Bye bye.